Okay, ladies and gentlemen, it's 9 a.m. It's time to start. We don't want to be late. First of all, I would like to say that Rafał, who is absent today, decided to make you more aware about Wrocław, which is great actually, because we probably never did it. So first of all, we would like to give you some pieces and parts about Wrocław, our beautiful city. So it's built on 12 islands, first of all. I don't know whether you are aware of that. It's often called the Venice of the North. It was even more beautiful 100 years ago, but we still do our best to make it more beautiful these days. So it has over 100 bridges connecting different parts of the city across the Oder river. Just as a starter, but Wrocław will not be the main hero of today. These will be people who will be presenting. So I would like to present to you John. John Lakos is a senior C++ architect at Bloomberg and author of large-scale C++. He helps shape the future of C++ actually as a key voice in the standards committee. Previously, he led library design at Bear Stearns and built patented tools at Mentor Graphics. With degrees from MIT and Columbia, he's also the co-author of Embracing Modern C++ Safely and continues expanding his large-scale C++ series. We always wanted to have some fun facts about our guest, so John likes his cheeseburgers, 30 seconds on a side. I learned, thanks to you, what it means. So it means that you are cooking a burger 30 seconds on a side, and it leaves the center cold and raw. My greetings to all the vegetarians, by the way, online and inside the room. But there will be a 10-minute break, just a reminder, in the middle of the talk, because this will be one of the longest lectures by John. Let me say, John has been compiling brilliance for years. Now he will be executing what C++ needs to be safe. Ladies and gentlemen, John Lakos, please make some noise. Thank you.
Thank you. Well, thank you for welcoming me here, and I'm looking forward to it. I think this is going to be a very important day because we've collected some very relevant information that's aggregated in the right direction to give you a nice overview of what we're trying to do, and then focus in on what you can do, and then what you can do practically, and then what you will be able to do. So I suggest staying for all four. I find them interesting, and I work with these fellows, and I will learn more as a result of this conference just by watching each of these independent people say what they have to say. So to begin with, I work at Bloomberg. This is the next level of bureaucracy beyond, you have the outer interface, then you have the interface, then you have the private interface. And this is the abstract. Presumably everybody knows what they're doing, so I'm putting it here. It's probably going to be on video, and so people can read what this is about. But it's not really important here because we're going to live this, and it's basically the state of the world and what we're going to do about it. So, introduction and motivation. I suppose people have noticed that C++ is under some scrutiny by various companies and I would say government agencies and people who are enthusiastic about languages that claim to be able to do things more better. And proponents of successor languages like Rust are saying, look what we can do. And there are good ideas in Rust, don't get me wrong. But sometimes, you see something really good and it's the answer to some things, but it's not necessarily the answer to what some people need very badly, and we'll explain what that means. So the regulatory agencies and the government cybersecurity organizations are getting the marketing that, and I'm not saying it isn't true, but they're receiving the message that we have languages that are safe. Why would we accept any other language that isn't safe, that doesn't call itself safe? So there's a problem right there. So we have bad marketing in C++, for sure. And major companies are backing away from starting new projects in C++. The first one was Google, and Microsoft has been thinking about it. In fact, Adobe has a plan to eliminate new functionality by 80% in the next 5 years. So this idea of moving away from C++ for new projects is a sign of something that we've not seen before. C++ powers the world, and 5 years from now, C++ will power the world. But the cost of getting interested, exciting people to extend what we have is not looking that good. And this is a trend. It's kind of like global warming. We're not going to die, in 10, 15 years. Unfortunately, I think the rate at which this is happening with C++ is on a much greater, faster trajectory. And so we need to do something quickly to do something to make it effective. So our top-level strategy, and in fact, my top-level strategy, which I started 3 years ago in my own head, is to reinvigorate C++, and to do so by getting general excitement out into the ecosystem, the design, the safety aspects, the efficiency aspects. And so we want to make C++ as safe, healthy, and efficient as practical as soon as we can. And safe comes first because that's what everybody seems to be latching onto. But we can't make C++ safe at the expense of our purpose in life, which is low-latency computing. Because once we do that, we're good for no one. So we have to be very careful that it's a Pareto improvement, and this is the difficult challenge we face. So 3 primary areas of focus. We have safety, and that's correctness, and it's security. At least, in my mind, if something isn't correct, it can't be very safe. If something isn't secure, meaning it's buggy and people can reach into it and steal your secrets, if you're in that environment, that's not so good. Then we have health. And by that I mean support for the compilers and the working elements of the system. We need to make sure that those things are covered. If they're missing and buggy and not up to date, the experience goes down, and that has an effect on the desire to keep using this platform. And then efficiency. There's nothing we should do to unilaterally reduce the efficiency of C++. C++ is the go-to language for maximal efficiency of everything. And as soon as we do something and take away that efficiency, would run a huge risk of allowing another language to get between C++ and the machine, and we really don't want to do that. There's also human efficiency. Right now we have things like allocators that in certain circumstances absolutely make code either run much more quickly or continue to run at the same speed that it did over many hours by minimizing a phenomenon known as diffusion. So allocators used properly are very important, but they're pain because you have to write them as library components and know how to use them. So there's more room to improve there as well. Okay. So what do we mean by correct? The essential behavior is as intended. Now, we can have a function that has behavior, but not all of the behavior is essential. There's something in the behavior that's important. So we want to make sure that our essential behavior is happening. And if there's some other behavior that we don't care about, as long as it's not too annoying, so be it. So we want to have support for detecting and creating defects. Secure, on the other hand, is we do not want people to steal our secrets easily, right? We want to make sure that whatever we write, it is designed well enough that somebody isn't going to do something sneaky, index off the end of the array, find some goodies, and do something with that. So there are all kinds of exploits that we can do if we allow that kind of thing. And putting safety checks on code mitigate that. So making C++ healthier ecosystem, having compilers, libraries, supporting tools like Clang, GCC, any of these things, it's going to make, if we have more money and more people excited about doing this, then this is going to improve the enthusiasm overall. Sanitizers, static analyzers, debuggers help people to solve problems. The better they are, the more high quality we have for our overall ecosystem. Testing frameworks and such. I mean, this is the bread and butter of what we do, so we want to make sure that these are available as well. And then making C++ more efficient. Well, we want the machine to be more efficient. We also want the humans to be more efficient. So things we can do to make the human more expedient, I'm sure AI is going to play in here. That's something we're going to want to do. All right. What do we aim to achieve? Make C++ easier to use securely and correctly. Close the gap with other safe languages. Blunt any desire to mitigate away from C++. Improve typical user experience. Send an example for other C++ organizations. By the way, I really do want, this whole talk is an advertisement that it shouldn't be just one or two companies trying to achieve this. This should be a consortium of people who have an investment in C++, who are interested in making sure that C++ remains the go-to language for the foreseeable future, for high performance, low latency code, and doesn't have the kinds of algorithmic restrictions that other languages like Rust and Swift do. Now, this is a big deal, because if you were going to go write in Swift or Rust, number one, you'd have to learn a different paradigm, different syntax, and then you'd have to learn about how you communicate those new languages with your huge code base of C++. And what Sean Baxter tried to do is say, no, what we'll do is we'll keep the syntax of C++, we'll write a library too, and it'll all be C++, you'll just have to write it in this different way, but it'll all be C++. And that might be a nice thing 30 years from now, but it doesn't solve today's problem that we have a whole bunch of deployed code out there, and we need to make sure that it is not UB-laden and risky. So, this is a medium to long-term project. So, that was a rather long introduction. This is basically what happened. This is from Timmer. He wrote a timeline for what sort of events happened during the creation of contracts. And what we have here are different events, as you can see on the bottom there. We had a proposal that was created and then departed with. Then we had a long series of papers, and then the papers ended. And then we had the first proposal from us, which was a macro-based contracts facility. And then there was another proposal that came along with it, and both of those kind of went away. And then there was a joint proposal that involved people like Strustrup and known people to do something that was in the language. And that continued for a while until 2019, when it got ripped out. And that was not good. It got into the language proper for a minute, and then it got ripped out. So we started SG21, and SG21 then went for 6 years. And it got approved by EWG and eventually made it into SG21 and then WG, and then eventually made it into the C++ plenary. So we have a working minimum viable product for contracts in the language. And we are here. And in about a week and a half, we're going to go to Kona and rehash this all over again, because trying to put a contracts language in C++ is remarkably hard, because not everybody sees the purpose of contract checking quite the same way. And that's because the way people would use contracts in different areas is completely different. For example, if you're in the my industry, I have to mention, contract checking can be absolute, where it says, if I detect a problem, I'm out. Or it can say, if I detect a problem, I'll let you know and keep going. Or it can ignore it entirely. Now, people who ignore it entirely, that's okay. They're done. They've already checked their code. They're happy. It's working. They don't want any expense. But there are people that want to check to see if there's a problem and then somehow continue. And they'll want to continue maybe because they're a financial services company. They'll want to throw an exception, which is risky because you've got all these no accepts out there. Could be catastrophic. But they want to at least try not to crash the system. And that's up to them. I'm not advocating that, but that's up to them. Then there are people that are nuclear power plant fighter jets, and they say, as soon as I know that there's something that I didn't expect, I want to fail fast using a quick assert. And so it'll check, and it'll trap in one stop, and you're out. And the other system that's watching your heartbeat will fail over. And that's the only way to do truly fault-tolerant systems, because you can't have a single point of failure be fault-tolerant, and a program is a single fault of failure. So there's that kind of very high-tech failover, whatever. Then you have video games and desktop publishing. And I think you know the worst thing in the world that can happen is you're right about to kill that monster, and because a pixel might have turned the wrong color, oh, no, can't have that, and the game crashes. That's not okay. Same thing, you have a paper, you've just about finished it, and something goes wrong, and it would have left a bad character on your screen. So instead, the whole thing goes away and you lose all your work. Those are the kind of situations where the very worst thing you can do is crash. So here we have a spectrum from you must crash immediately to try to limp along a little bit, save your stuff, and then get out, and just keep on going. Maybe don't even tell the user. And since these are all valid uses of contracts, and contracts have to be for everybody, what's more, contracts have to work on bad code. So even if your code is really bad, you need to be able to annotate that really bad code and then help it to become better code. But if you insist that contracts can work only on perfect code, it misses the point. Because contracts have to represent what is, no matter how bad is. So anyway, that's a little extra background on this is what happened. Herb Sutter, by the way, gave a very good talk, and well recommend you listen to it. It was fairly balanced on the pros and cons of contracts. I happen to not think that there's much balance at all. We've worked on contracts myself since 2003. They've been in production since 2004 in their moral state. They've been refined and refined and refined for more than a decade in the Standards Committee itself. So I'm willing to say that they're pretty ready to go. And anything that we had any doubt about, we left for the next one. That's why it's called a minimal viable product. If there's something we couldn't decide on, we left it ill-formed, which means we can always add it later. It's one of the beautiful things. When in doubt, do without. And we did without for things that we were absolutely sure of, but one person was really unhappy. So we said, okay, we'll wait, because it doesn't stop the value of the thing. Anyway, so this is what the BDE team, by the way, has done during the course of its internal, BDE is my internal working group. And during the course of time, we were doing various things. And right around 2015, we realized that we needed something different from just assert. We needed something that in the code didn't terminate the code. Whereas assert terminated the code, it was like enforce. We needed something to observe the code. So we had assert and review, that became enforce and observe in the new. But the same thing. The idea being that we could put a check in because the code is old and it works, put a check in, and if it fires, we get a report that something's wrong, but the client isn't inconvenienced because the client's been happy for 2 years. Why today of all days does the client crash? So this is something people need to understand. There's a difference between old code and new code. In new code, we crash it, psh. But in old code, it's a different story. Now, if you think about it, when you start to pepper these programs with these contract checks, they're pretty good because they've been seasoned. But just like an apartment building, you turn on the lights in the middle of the night, you might see a few cockroaches. Now imagine if those lights were like high power ultraviolet lights. You turn them on and whatever cockroaches are out that night, psh, they're gone. And then the next night you do it again and they're just a few the next night. Psh. So the third night there's like one. Psh. And then the fourth night, nothing. And the fifth night, nothing. And then the sixth night, there's one little baby cockroach crawling along, psh, gone. And then it might go for a week and you don't see anything. And the point here is that the cost of actively checking stays the same, but the return on investment goes down. Why? Because you're not checking for input. You're redundantly checking to see if the code that you wrote is bug-free. And once you have bug-free code, all the contract checking in the world isn't going to help you. So, seasoned code is less buggy than unseasoned code, and seasoned code that has been thoroughly contract checked is better still. Just saying. Anyway, we realized that right around then, and then we started writing papers, Josh and I, and around here we were sponsoring the 22x features in Clang by Jabot, and he was starting to make that happen. So it was right around 22 that Bloomberg got involved in helping the efficiencies of these compilers. And then we sponsored more things, and Timur got involved, and then more things, and eventually Sean Edwards, who is the Bloomberg CTO, made it official. Bloomberg is going to support the ecosystem and the prototyping of new features. So Bloomberg is a player in this, and I'm really asking to get other people to be players in this work. All right, so this is what it looks like when we make sausage. Get an idea, it sits in the proposal world, and it blows up. Okay. Then we get another idea, make some progress. We start to do a little bit of prototyping, and it blows up. And we still do yet another thing, and we use the old prototyping to help us along our way. We learned that the prototyping was good, and we get something in the proposal area, and it gets it into the standard. This is where we are now, and hopefully it stays, and then hopefully it'll go down to production compilers that can be used, and then hopefully they'll get integrated into our work. So that means starting with this, took 5 years to get something out, it took a year to get it into the standard, and it's going to take 4 years to get it from the standard into our code base, for a total of 10 years. Okay. This would be better if things were just a little cleaner and we just did stuff straight. This way, we start with something, we end with something, and it's 2 years maybe to get it into the ISO standard, and then maybe 1 year before that thing gets put down into the compilers, and maybe 1 more year of integration. And here, we're talking, right, 3 years. So this would be ideal. What we're saying is, as soon as we know that the thing hits 26, we have all of our most likely compilers that we can start fitting with our production code so that there isn't any surprise. So when it's officially released, we can pull the switch. Hope that was clear. Okay, so next, what does it mean to be safe? Different things to different people. So secure doesn't admit security vulnerabilities. Well-defined doesn't admit undefined behavior or crazy things. Correct behavior does what it's intended to do. And what shocks me is that, in my experience, does what it intended to do is the least of people's concerns. And it's what I strive to do. So I'm a little confused, let me say, as to why I'm in the minority here. But if you get things right, it sure helps, because if you get things wrong, that's how you lead to security vulnerabilities. Oh, excuse me. All right. So memory safety. A language is memory safe if it does not permit access to unallocated or uninitialized memory. And one other thing, it has to be in the right type. So this is a reasonable definition of memory safety. And we could, of course, write something to something that's uninitialized, but we can't read something that's uninitialized. Just trying to fill in all the dots. So garbage collected language like Java and Python, JavaScript, Go. Those are languages that do memory safe things. Functional languages, Scala, Camel, Haskell, PHP. Languages that enforce the law of exclusivity. Rust with a borrow checker, and Swift 6.0 with lifetime via reference counting. So these are things that try to do this extra memory thing, and saying something is memory safe is like, oh, it's got the seal of approval. This is great. Now, you know this is highly problematic because people don't tend to write Rust in safe Rust exclusively. Does anybody know why that's the case? Do they want to throw out why? Why don't we just write safe Rust and be... Yeah?
In my experience, it's because you got to connect to other libraries written in C or C++.
So what was said is, we could write safe Rust, but for we have to connect to other libraries that are not written in Rust. Is that what I heard? So my understanding, not being a Rust expert, is that the way Rust works is it disallows a large subset of the algorithms that we use in C++ because the compiler is not in a position to prove that there are no race conditions. Certain data structures, like tree-like structures, are more amiable to doing that than linear lists. And again, I'm speaking from second terms. So you have unsafe regions in Rust. The idea, I'm told, is you have a lot of safe regions in Rust, and then you have a few unsafe regions, and people look really hard at those. Okay, that's just to be clear. It's not that the language is safe. It's safe in the easy places where it's easy to be safe, and in the places where it's hard to be safe, it isn't safe. So you have to do something else. The sad thing is that the goal we ultimately want to achieve is that even in those very hard cases, we would still be able to detect at runtime that a bug is about to occur. Now that's a big ask, and that's something that's a body of research, and I'm getting way ahead of myself. But I'm just pointing out right now that there's a lot of stuff that's stated and people buy that's really quite a pill to swallow if you follow it down to its base properties. Rust has a very good marketing environment, and C++ has a terrible marketing environment. So just know that. We're trying to make the marketing environment the true, based on truth, marketing environment step up with the Rust marketing environment. Truth or not. Okay. And this is basically just what's necessary for threading. Okay, what memory safety isn't? Memory safety does not necessarily imply the absence of all undefined behavior. Here's an example. This is guaranteed undefined behavior. So this is UB, but it's not a memory safety violation per se. Right? So we don't say memory safety equals safe system. There may be safe systems that have memory safety, but memory safety alone does not imply all things. It implies a subset. What are we trying to achieve? Security. Every C++ program can be built such that no core language UB is ever executed. Think about that. Some way that we could turn on the compiler so that if the compiler were about to do a segfault or a whatever, it instead called a handler and said, hey, you're about to do this thing. What do you want to do? Now imagine if you had a program that had integer overflows and you wanted to catch those. What would you do? You set a flag that says, catch those integer overflows, and every time you do, report the location, file and line number, and time, and keep going. And you get this report, and you send it to your programmer, and they fix it, and then you observe it later, and it's not there, and the bugs went away, just like they did in the room when you turned on the light. I don't see how that can be wrong. We should want that. That's coming. That's an obvious improvement. Okay. Let me see. Am I going the wrong direction? Looks like I did. Okay. Correctness. User-defined functions can be written such that their plain language contract preconditions and postconditions are optionally checked redundantly, typically at runtime. So here what we're saying, we expect you to call this function under these conditions. And we don't have to check you every time, but maybe when we put this program together the first time, we're going to check it. And if there's a problem, we'll let you know. Or we could not do that, and you're going along with a program that's not put together right, and that can take a long time. The idea is divide and conquer. If you have a program that has 10 subprograms, first make sure all of the subprograms are working and do them in the order of levelization. For example, if you had 4 level 1 subprograms and then 3 level 2 subprograms and then 2 level 3 subprograms and 1 level 4 subprogram, form this nice triangle. Make sure all the level 1s are working, then make sure all the level 2s are working, so on and so forth. And while you're at it, put the precondition checks to make sure that the calls from the level 2s to the level 1s are in contract. And this is just more ways of functionally checking that your code isn't wrong or a way you didn't expect it to be. Okay. I just want to mention that plain language contracts are for humans, and contract checks, those are for machines. So something that you can't This is like what can't be checked. Not everything in the code is directed at the virtual machine. So, for example, if the human caller has purchased a license to use this particular package of subroutines, none of that is going to necessarily be part of the virtual machine's data. Yet that could be a human contract. So not everything in a human plain language contract can be inserted into the machine. But I digress. Most can. So, what we'd like to do is, without changing any source code, if we can simply recompile and relink our code using an ISO-compliant compiler, we can be sure that no core language UB will ever be executed. This is a goal that we really want to strive for. And as I said, it's going to take some time. We're working on it. How am I doing on time? I have, 7 minutes before the break? Ish, okay. So, again, without changing any core source code, no source code language UB will ever be executed. If we could do that, then that means all the code around the world would be benefiting from this release of C++. We could just recompile it and learn. Correctness. We want to make sure that if you want to take the time to put in your narrow contracts or contracts that have preconditions, if you want to take the time to annotate your older programs with the proper preconditions, you can do so and achieve exactly the full checking without having to change the behavior of the function. So this is, again, very important. In any other approach, we either have to go to another language or we have to go to the same language but rewrite our algorithms. In this approach, we're adding notation, consistent notation, which we can do incrementally and selectively. So conforming standard library implementations will detect and report this as well, with no change to client code. Okay, tools that abstract UB in C++, address UB in C++. I guess I'll start this now, and we might have to stop in the middle, but that's okay. We have 6 minutes. So there's no one tool in C++ that can get rid of UB. UB is undefined behavior. Undefined behavior allows the compiler to do pretty much whatever it wants, since it knows that undefined behavior can't happen. So it gets a free lunch, can do whatever. So runtime contract checking is the first thing, and we do that. Erroneous behavior is the second thing, and we do that. The third thing, symbolic contract assertions, is something we could do. We don't do that. Source code subsetting is something that we could do. We don't do that yet. Fifth is compile time enforced exclusivity. That's what Sean Baxter tried to do. We don't do that yet. And runtime enforced reference counting. And that's what Swift 6.0 does. And we don't do that yet either. But those are things that are on the table to look at. So, safe contracts. What is a contract? Plain language contract, natural language description of an agreement between the client and the library. A contract assertion, a C++ code construct that identifies something that must be true in a correct program. So one of the things we observe is, if you have a program and you have a contract assertion, if the contract assertion fires, your program is broken and a human being has to fix it. That is kind of by definition, because either the assertion is broken or the plain language contract is broken. 26 contracts MVP, precondition erosions are directly on declarations. The only thing that makes this contracts facility even remotely different from other contracts facilities that we use all over creation is that we have the pre and post conditions on the declaration. Now, that is a trivial syntactic addition. It makes it easier for code analyzers, static analyzers, and others to not have to know the implementation to infer things. It's a good thing. But it's certainly nothing that compiler vendors are at all scared about. Yet, it is a matter of contention because there are a few people who are still concerned about contracts, and I do mean a few. So there's a standard way to set the contract violation handler. That was the most important reason, because if everybody had their own handler, you'd have to go look on your program stack, your software stack, to know which tools you're using and set their individual handlers. You wouldn't want to do that. So it's much better that there's one handler to set per process. And the idea is that every application owner gets to decide what the rules are for checking. They can be all off, they can be all on, they could be any combination of the above. They can have any semantics that they want because they own the program. And there could be a very similar program over here that has a very different set of settings. But remember that in a correct program, contract checks do absolutely nothing. Nothing. So, these are the 4 currently approved semantics. Ignore, do nothing, enforce, call the handler and terminate. Observe, call the handler and don't terminate, just continue, hope for the best. And quick enforce, don't call the handler, just trap and get out. And there's a 5th semantic that's anticipated. It's called assume, and right now we have it for all the operators, because if you overflow an integer, or if you do something like divide by 0, or dereference null pointer, you're going to get UB, and the semantic for that in the language today is assume. Okay, simple use case. Are we at that time, or are we still at 2 minutes? 2 minutes? Okay. So here's a simple case double square root. Return the value when represented as close as possible to the positive square root, the specified x. So this is a function declaration. This is the essential behavior. This is the undefined behavior. Okay? Those are the 3 parts of a contract. They're pretty standard. So as close as possible, this is the plain language contract. So you want to say that pre x is greater than or equal to 0, because we don't allow negatives. We say post, this is the notation. We're going to capture r. We're going to say r is greater than or equal to 0. And I'm just saying, recall, here's kind of hard to read, that you can get the next iota using this function. And so we didn't put in all the text for it. So you can do something like this, and then you can write something like this. And what this is basically saying is, I'm going to multiply the thing, and if the thing I get is bigger, then the one less one is going to be smaller, and if the thing I get is smaller, then the one greater one is going to be bigger, like that. And that's just an extra check, because if that weren't true, then this wouldn't be correct. So I'm going to stop there, and then after our break, I'll say this again, and I'll go to the next slide, because that's a good one to repeat. So before the break, we had this square root function. We wanted to add a little bit better post condition function. We started with this thing that's pretty boring. We said, wait a minute, if r times r is less than or equal to x, and the next after 1 squared is greater than x. So in other words, it's saying that if this thing is on the small side, then the other one should be on the bigger side. And similarly, if this thing is on the bigger side, the other one should be on the smaller side. I hope I got that right. But there's a problem with this. It doesn't quite capture everything, because what could happen is the one on this side is on this side, and the one on the other side is on the other side, but it's closer. Its absolute value is closer. So this would be wrong by the spec. So what I want to get across in this particular example is that post-conditions form a kind of checking called property checking. Property checking is notoriously hard to write and get right. In my opinion, when you can, you write unit tests to do value-based checking by just putting numbers in a systematic way. The third volume of my book, Large Scale C++ Verification and Testing, goes into this in some detail and will explain why this is generally a bad idea. But, and I wanted to mention that whenever you're trying to look at the post-condition of something, you have to actually do this horrible const thing. Timur will explain it in the next talk. It's one of those things that happens, and it's ugly, but I'll skip it for now. Is this post-condition good enough? And the answer is no. It's not good enough if you really care about what the thing is doing, which is why we don't do things this way. But I'm just going to show you what can happen here. Look at this. The way this is written for now, it's make an assumption, just for now, that the thing is above the square. And it's going to turn out, if you just reason through it as if that were true, then you realize that if the thing is below, the thing that's been checking will be negative, and it will give you the full result that you want, meaning that the original thing returned is as close. The amount of work I had to do to prove this to myself is embarrassing. But the point is we could have just checked it using value checks. So this little digression is, we have postconditions in the language, but honestly, preconditions are what allow you to assemble the blocks. And we've been using preconditions for 20-something years. We don't have postconditions. Not saying postconditions are useless, but the return on investment is nothing compared to the return on investment of preconditions. So having said that, oh, and one other thing. If you try to do the other one where you test the squares and you go into the subnormal range, it loses all accuracy, whereas this one's pretty accurate. But just finding this stuff out is like a small master's thesis, so I don't... Anyway, most important usage for these things is putting precondition check on bracket operators. This is what we really need to do. This is where most of the bugs occur. And if we did this, a heck of a lot of security violations on the standard libraries would be detected. So I think that's an important statement. Why do you think we might call contract assertions ghost code? Anybody?
It's code written on your behalf and executed on your behalf without you actually...
Okay. So the code is written on your behalf and executed on your behalf without your actually calling it. Sounds to me that templates could have some, ghost code in them. I think the purpose, what I mean by ghost code is, it might be there, but you can't touch it. It can look at you, but it can't touch you. So ghost code is a layer on top of regular code, and the idea is the ghost code is there to observe and maybe complain, but not modify. So contract checks are ghost code. That's what we mean by that. There's also a levelization implied. So, how hard is it to teach contracts? I want you to know that contracts are studied probably more than any other thing, even maybe concepts, but we can debate that. And they've had more deployment experience than anything else in creation. What do you need to know? What do you need to tell a student to use a contract assertion? The first thing you tell them is tell the truth, write something down that's true, period. Just, it's true. And then make sure that while checking that truth, there are no side effects. That's it. Literally, that's it. That is all you have to tell a kindergartner. And you're done. Now, when they get to be an expert, or think so, no assertions, predicates, should have destructive side effects. A destructive side effect alters essential behavior. So let's give an example. If I put a print statement in a pushback for a vector, that's ugly. But it doesn't alter the essential behavior because the essential behavior in the pushback never said that it wasn't going to print a message on the console. So when you're trying to avoid things you don't want, that's called quality of implementation. But when you say, these are things I do want, like I want you to print out my tax form, and then if a printf comes out in the middle and does psh, that's affecting essential behavior. So, side effects must not affect essential behavior or they wreck the program. That's it. So there's the easy and the hard way. The easy way you can teach a 5-year-old, and the hard way you'll have to talk about it. Anyway, I think it's as easy to teach as could possibly be. Okay. Just remember, essential behavior, we don't mess with essential behavior. Destructive side effects mess with essential behavior. Coming in C++ 29, we're going to have the ability to change the ways we enforce things, make contract assertions that are expensive audit, meaning we can have them on only in special cases. Capture input values and use them as post conditions so we don't have to make that darn thing const. And employee requires classes. So here's an example, future example of enforce. Here's another one. Capturing values and requires clause. And the requires clause simply is something good for templates that says, if your thing doesn't have this thing, then don't worry about it. It's like if your arms have to be smaller than 6 feet and you don't have any arms, okay, you're all right. Anyway, that's the idea. That makes template programming a little bit easier. Now, assertions in the core language, implicit assertion checks. That means that when you have an operation, just a plain old integer overflow, divide by 0, whatever, you can implicitly set what happens. Do you get a callback? Do you get a trap? Do you get whatever? This gives you control over whether your program is, super high security or friendly, telling you, your numbers, you might want to use long ints here or long ints here because your integers are overflowing. And it's just a nice reminder, and you get it for free by hitting a compiler switch. How can anybody be offended by that? It's just asking the compiler for help and just a warning. Or you could stick with the bad behavior. Anyway. Same with siege style array bounds checks. We should be able to check these things to the extent we can. Now, we can't check everything yet, and that's why we need more technology, and that's what we're going to hear about later in this series. Okay. So we could magically check for these things today. We could go and write some code. And in fact, some people suggest we should. But we get them for free with no changes to our source code. Just look at this paper that we're proposing. And note that this can be available much sooner than C++ 29 because all of this is about undefined behavior. And undefined behavior doesn't need any permission from the standard to change because it's undefined. And so we might get it next year. Good news. Erroneous behavior. Here's a fun one. How many people have heard of erroneous behavior? Not a whole lot. Okay. So erroneous behavior came out of the attempt to fix a known bug where somebody tries to read a variable that hasn't been initialized on the program stack. And one of the solutions was to just say whenever you put an integer or double or whatever on the program stack, just set it to 0. Okay, and make that part of the standard. What's wrong with that? Anybody?
You're paying for what you're not using.
Okay, so there's slight overhead. And they made the case that the overhead was slight, specifically in the case for a 0-bit pattern. But it's actually much worse than that. It's much worse than that because if you define it to be 0, then all the bugs that have been created over all creation are now masked because they've been grandfathered in as intentional. We don't want to do that. When somebody did that originally, they made a mistake. And what you're doing is you're blessing their mistake so that no longer can a sanitizer catch it. Now it has to be a human being with deep knowledge of the purpose of the program. So we don't do that. So what we did do is we said, it's still bad, not good, but it's not undefined. It's what they call loosely defined, meaning it's a number. It's not an indeterminate number. It's a number. But you don't know what it is. And it could be a different number on every invocation of the program. And in particular, if it's a test program and it were floating point number, we might give it a signaling NAND. And if it were a regular production program, we might give it a 0. You see what I'm saying? In other words, we can change the value and try to detect the instability. So that's what we did. So an erroneous value is a value that's wrong, right? Erroneous behavior is behavior that leads to something that's not good, but you can't time travel on it. You can't make the program arbitrarily crazy. It's just a wrong number. And that's one of the things of the 3 things we try to do in safety. We want to get the right answer, for sure. If we have if we have an error, rather than UB, we want EB so that the flat tire doesn't cause the car to explode. The flat tire is just a flat tire. And we want to make sure that there are no security holes so somebody doesn't steal the car. And those are the 3 kinds of things we're trying to guard against. Anyway, so erroneous behavior is particularly good when you don't have the time to check. If you put a cheap value in for production, because you put expensive ones in for debugging, often the compiler will be able to see that that's just dead because it's going to get loaded before it's stored, before it's read, and so that will get optimized away. But if it doesn't get optimized away, it prevents leaking the secret. So that's what erroneous behavior does. Anyway, what did I do with my thing? Is this it? This is it. Okay. So this is what defining undefined behavior does. To guard against security vulnerabilities when contract violations are not enforced. EB is nonetheless still guarded by a precondition. So you can have EB and you can have a precondition guard it. And then if the precondition is active, it says, bad. But if you don't have a precondition, this still protects you from the worst damage. The car may have a flat tire, but it won't blow up. And it remains objectively and observably incorrect. We didn't hide it. We didn't grandfather this bug. That's important. All right. I'm just going to put this up here. Let's see. Oops. I think I'll just put this up here as an example to look at. Anyway, this is the idea. We no longer have UB, we have EB. Okay. So here's a little bit of putting things together. We started with runtime checking and Roney's behavior, and signed integer overflow is a little bit of both, but there are other things that we can't handle. So symbolic contracts assertions are one of the ways we could possibly try to do something, but these are ad hoc approaches, and we're trying to come up with something that's a little bit more systematic. So symbolic assertions here, if you notice the pre with the symbolic, it says, I want those two things to be able to come from the same block of memory. That's what F wants. And when it sees this, it says, the compiler says, no. You advertised that you wanted them to come from the same block, and I can see from my code that I'm not giving it to you from the same block. So at compile time, this is no good. And this is just a simple example of the kinds of things we want to do, but not this way. This is just a technique, but it's an ad hoc technique. What we're going to, when you wait till you see what Gasper has to show you, what he's going to show you is like the nuclear weapon of all contracts. And that's to see. But you need to first see how good this stuff is without it. Conventional contracts are very good. Nuclear contracts are coming. Okay. So here's a standard example. Since I am kind of running out of time, I just want to give you a gist of these. These are not things that are in the standard. These are things that could be in the standard. So a standard iterator, for example. This is inherently not runtime checkable because we have a pushback in the middle of our vectors. So it's not really easy to put in some sort of static checking and have it do something useful. You see that this line here kind of mucks things up? Now, this is where things get a little harder. Profiles. So profiles are something you may have heard about. There's been a lot of discussion about it. Bjorn Strustrup thinks that profiles will be the answer to things, and I think that there are things that are the answer to things, and sometimes they get put under the moniker of profiles. But actually, I think what we're talking about is creating subsets of allowed code, which we might call epochs. There is value to that, because maybe there's some code we just don't want people to use in this area. That's an organizational choice, and it's orthogonal to contracts. So anyway, this is something we might want to do. So this is a big one. Exclusivity enforced at compile time. This is what Sean Baxter and Russ do. And they, at compile time, say, no. We're gonna run this thing like a military base. There's gonna be no hanky-panky and sharing and And they do it in a very, well-defined way. And here's the law of exclusivity. If a storage reference expression evaluates to a storage reference that is implemented by a variable, then that formal access duration of the access may not overlap the formal access duration of any other access to the same variable unless both accesses are reads. You kind of know what that means, one writer or multiple readers. And this is just what that is, and it does it at compile time so that if there are any paths that would violate this, it rejects the program. And it's very cranky because it's not going to allow, no matter even if I reserve 1 million things, it's not going to allow this program to compile. Just not going to happen. So we can't write that. So it's not useful for legacy software. That's the problem with Sean Baxter's stuff. It's amazing. He's a genius. And yet, I can't use it for my use case because I have a ton of C++, and many people have a ton of C++. Just Just look at other companies that have been out there for a while that have written C++ out the, and they're not going to run to Rust, so that's not going to happen. So reference counting enforced at runtime, this is a little bit more like what Swift 6.0 does. It does more like garbage collection, automatic reference counting. And what happens here is it has the capacity, unlike Rust, and it's not using a different vector for this, and it can just do it. I hope I've got it right here. Yeah. Now, there's another thing we can do. We can protect something with preconditions, so even internally you don't even see the, oops, we had a problem. So you can put the precondition up here. Now, because this precondition guards what could go wrong there, that can't even happen. So preconditions can guard you be at a higher level and really just say the client was wrong for even calling this. Okay, so B cannot be invalid. What is ghost data? Optional information made available to multiple contract informations at various granularities, e.g. all assertions within a particular function invocation that would not otherwise be represented in the abstract machine. Why do we call it ghost data? Any ideas?
Store the information.
What?
Just store the information for acknowledge the user what goes wrong, but we don't mess with data.
So it's additional information to do what?
Just to gather the information about what went wrong, and we not mess with the business data.
Okay, so it sounded like you said information, gather information about what went wrong. That sounds like logging data. What ghost data is, first and foremost, is it might be there, it might not. Nothing in your program depends on ghost data. Ghost data may depend on your program, right? Ghost data can be affected by ghost functions, read by ghost functions. In other words, there's this spooky area that haunts your program with ghost data and ghost functions, and you don't know about it. You just go minding your own business, like you're a circus, actor on a wire. You don't know if there's a net. There might be a net. There might not be, but you don't know. You just keep going. That's a really good analogy. But it turns on if you are in a program that has enabled ghost builds of ghost code and ghost data, they might be able to determine that you are about to execute undefined behavior and do something about it. Or not. You can't write your code assuming that it's there. But the idea is that ghost data is above and beyond data that's stored in the virtual machine. It's extra data. Think about what sanitizers do. Does everybody know what a sanitizer, like thread sanitizer, those kinds of things? Anybody? One person, two? Okay, sanitizers are tools that go in and take an executable and instrument it to do exactly what we're talking about here. But it's a global operation and it's extremely expensive. Imagine if what we could do here was local, modular, regional, and hence scalable to any size. What would that do? Anyway, this is why you're here at this company. So I'm supposed, what? I heard somebody say something. No? My imagination. So we want to stop for sure in 7 minutes. Is that right? Okay. So more essential properties of ghost data. With ghost data, we can express any requirement whose violation could alter program behavior. Many assertions will be core language interfaces will need core language interfaces to update them. And ghost data has 0 runtime overhead when contract assertion checks are disabled, which means once you've turned on the lights, enough, You can turn it off and there's no cost. And don't tell anybody, but in someday in the future, you might be able to have the contract assertions assumed and your program speed go up. Just saying. That makes some people crazy. You don't have to do that. The other thing is, when local analysis can prove that the assertion will not be violated, then some of the intermediate steps can compress. And there are people that have a goal that think that writing code a certain way, you can compress almost all of those steps. So you can go from where you're writing Rust-like code with no overhead, with no runtime overhead, to, really sloppy C++ code with all kinds of runtime overhead for checking. Not for performance, as I said. Once the C++ code is checked, it might run twice as fast as the Rust code. So we have to remember what we're talking about with speed. Anyway, it's an active project. We have Lisa Lippincott, Josh Byrne, and Gasper Asman, and the Mongo Gill at the C++ Foundation. And anybody who's interested in joining us, I would be very happy for you to email me and tell me how you'd like to work with us. That's really the point of this thing. And Gasper's the fourth speaker, and he will blow your mind, I promise you. He did mine last night. I'm still trying to recover. I'm a little shocked. So, just some current safety projects. These are the different kinds of things that we get with memory safety. But I did want to finally, I think this is where I'm going to stop, because this is a good slide to stop on. This is where we were. And then we have symbolic contract checking, we have profiles, we have unallocated memory access, we have data races, and we have compile time exclusivity, which does a really good job on a lot of stuff, but not everything. Then we have runtime reference counting, still uses compile time exclusivity for data races, but it gives us a little bit more breathing room with the kind of algorithms we use for lifetimes. And then we have ghost data that takes care of all of it. And so I'm going to stop here, because this is my favorite slide, because this is where we're going. So, yeah, I have a lot more material, but we'll get to it someday. So we'll stop there for questions.
Yep. We're ready with microphones, so Rafał, together with Tomek, if I remember correctly, yes, are ready to just jump all over the room. I'm just standing in front of the stage, so you don't have to lit me up, actually. But definitely, it will be the time for your questions. The questions from the room will precede the questions from online. So we are starting with you, just to thank you for the presence, first of all. So please raise your hand. Just let us know that you would like to ask something. It's actually the best moment to ask one of the people who are the architects of C++. So we will appreciate your hands being raised. Just let us know. We're starting now. So let's just see if you have any. If not, then we will jump straight to our online. But there is a question. So Rafał, one of our gentlemen seated over there. Oh yeah, please do. The microphone is yours. Thank you.
Okay, so you've showed us the way that we can analyze the functions per se. But can we do such an analysis for whole project, just not to mess up with our code's existing one that already exists?
I'm not sure I quite understand. I think what you said is you have a whole project.
Yes.
And you're asking, could you use what we have on your whole project?
Yes. For example, I would like to ensure that on my whole project, I will not divide by 0 anywhere.
Okay. So what you would do is you would rebuild your project with a compiler that had a switch, because this is all compiler switches, but they're standard. right? There's standard compile, like enable, like ndebug, those kind of things, right? Standard. You just say, I would like this semantic to occur for that undefined behavior.
Exactly.
So that you don't have to do anything to your code other than recompile it with that switch.
Okay, thank you.
And yeah, it's pretty amazing. Yeah.
First question asked, but we would not like to refrain from asking more. There's another gentleman seated at the front. Please, the floor is yours.
Hi, great talk. I was wondering if the contracts can be validated so that you know that something isn't going to fail. Can everything be no except then, or?
Okay, so the question is, can the contracts be validated so that they don't fail, and then something about no except?
For instance, if like earlier, like if you can guarantee a function that takes an argument doesn't divide by 0, for instance, and you know that would be the case throughout your program, can you treat those functions as no except now because you know that they won't throw?
Okay, I think I'm going to try to rephrase the question. Well, first of all, I'm going to say, no except was created for one purpose and one purpose only, and that was move. Period. And move can't throw because if it throws, it can't do what it needs to do. In other words, move was created so that we would have an optimization, but the underlying trust was that you wouldn't get halfway through moving your vector elements and then have something throw when you couldn't go back and you couldn't go forward. Now that use of it got exploded into, oh look, I can make my code smaller by not having this be, making this no except, but not faster. Because the way no except is implemented in modern compilers, all of the extra code goes in a page that's never loaded unless you have an exception. Bjorna regrets how much use of no except is out there. And if it were to be done again, the only use of no except would be move. Because the thing is, if you want to throw an exception, that might be the only way to save yourself, to get to a place to recover in certain, not necessarily good designs. But remember, contracts are for all designs. We wouldn't do it that way. But we would not use no except where no except is needed, which is move. What can I tell you? I don't know if that answered your question, but I would not use no except just because you could.
Okay, thanks. Yeah, cheers.
Thank you for the question. I hope you're just meeting somewhere in the middle of the road of requiring information and providing information and speaking the same language. If there are any more participants today who would like to ask, there is somewhere back there. So we'll just give a moment. Please remember, you can still ask questions online. This is the best moment just to remind you, this is not the only option right here. It will be also throughout the rest of the presentations. The microphone is on. The floor is yours. Thank you.
Okay, so I have two questions. First one, did you actually calculate what can be overhead of runtime execution of turning on this safety mechanism, ghost data contracts? And second of all, is there a chance to turn it on only for a part of the code? So I have part of the code that should be safe and part of the code that needs to be extremely efficient. And
Okay,
I want to run it in only part of the code.
I think the answer is, in practice, for 20 years, we've been running certain code in production and certain code not checked. So in other words, what you want to do is you want to have kind of like spheres, where there's the outer part of the sphere, which gets a lot of direct impact. Those are checked. But internally, like in the kernel, that stuff works. So we don't have to check that every time. So I think the thing you're trying to ask is, can we selectively pick the heavy traffic places, heavy connections where people are kind of traveling through, use it, versus people who have been the same forever, nothing's changed, and there's never any detection. So it's yes, you can have it in separate places. That's right now at the translation unit level for 26. For 29, it will be at the individual assertion check level. Okay? So, and as far as measuring it, my suggestion is measure it. And if it doesn't bother you, use it. And if it does, tune it or whatever. But whatever cost it is, remember the purpose is not, first get it right, then make it fast. So once you get it right, you turn it off, it's really fast. Okay?
Thank you for asking once again. We still have some time and some ground for questions. There's again the question at the front and even in the middle. So
I have
let's start there.
a more philosophical maybe question because as we can see in Rust, there are some libraries which demand some checks, and then people implement something and they violate that with unsafe switches. And if we implement in standard library some more checks, what is what can we do to guarantee that people obey that checks and not violate them just to write faster and produce code in a faster manner, but violating those more safety improvements?
Okay, I'm not quite understanding. We have contract checks that say you must be this or you're out of contract. Then we can turn those checks on or not. What are you, and let's say we have a standard library that has those checks. Are you saying that as a developer, you would disable those checks?
Maybe not as a final developer, but in some library which is between me and, for example, embedded environment where that would be some kind of useful. Useful in the in the wrong way. Yes.
Well, the person who builds the program, person who owns main and builds the program, makes the decisions. The person who's calling the functions, they don't know anything.
Okay.
So ultimately, it's the person who owns main and who builds the program, who owns, he's the program owner. He or she gets to make that decision.
Okay.
Okay?
Thank you.
Sure.
Thank you so much. We are left with 3 more minutes, so I will be the policeman just watching that this is the last question from the room, and there's another online. Thank you.
Hi, could you please comment on how it's going to coexist with C libraries that are used in the project?
C libraries that have C assert.
Yeah, but the C++ well, contract checks are not like a part of C. So if I use code that well, also compiled as a part of the project, and it's a C code, so how are they gonna match together?
Well, you can imagine that the C code will do what the C code does, and the C++ code will do what the C++ code does, and there's even a proposal for 29 to make C assert play with our handlers. But unless you do something deliberately, anything that has C assert in it, the entire program has to be ndebug or no ndebug. That's just the way C stuff, that's the way it works. Now, with our code, that's not true. So you have more flexibility to turn on any subset of our assertions. So you have more flexibility, but it doesn't affect your flexibility with C at all. You see?
So completely independent.
What?
Independent.
They're independent. They can be made less dependent, but until you do it, they're independent.
Okay, thanks.
Sure.
Thank you for the questions from the room. That will conclude, let's say, the internal space, and now we're just moving outside where our online colleagues are watching, and there was a question. Rafa will read that.
I hope you can hear me.
Yes.
This is the very first question in our application, so
Congratulations.
yes, and it was passed even 40 minutes ago. So, John, over to you. Checking the data with assertions is pretty easy. What about checking functions or lambdas passed to a function or implementation of the virtual interface?
That sounds like a tongue twister to me. The question that I would give back is, could a human being, looking at the code, determine whether the standard says it's undefined behavior? If the answer is yes, then we can do it with sufficient data. If the standard doesn't speak to it, we can't. The whole point is, with sufficient information, any question can be answered. And the challenge is to encode that so that we know what we're in for. But yes, it's harder. There are things that are much harder. There are things that are much easier. We already did the easy things. We're working on the hard things. But see the talk at 3:05, because that will explain how really hard things get propagated.
Okay, thank you. I think we are at the top.
Okay.
Okay, I hope all the questions were answered, but definitely above everything, I hope you really had a good time spending this with one of the C++ architects at Bloomberg and author of large-scale C++. You can read way more, of course, on Pages, but it's better just to come up to John and maybe to speak to him, because there's a great chance to do that. We are in for the coffee break, but hey, guys, let's just give a warm applause to John Lakos.
Thank you.